Hello, and welcome to the Labline Electron Beam Evaporator Training and Information Guide. This presentation is meant to give you an introductory overview of operating the evaporator so that you might minimize the amount of necessary training time. Electron beam evaporation involves focusing an intense electron emission at an element or inorganic compound to heat it to temperatures sufficient to evaporate at a desired rate. During this, a hot filament emits electrons, which are steered by both permanent magnets and coils so that they exclusively strike the desired evaporant. These are some views of typical electron beam evaporator components. This is the full assembly. This round component is what's called the hearth, and the holes in it are called pockets. In the pockets sit crucibles which are filled with the desired materials. Underneath the evaporator, there's something that looks like this, which is called the emitter. The emitter is what generates the electron beam that is focused into the pocket. This is a side view of the entire assembly. The hearth has a plate which covers it, so that only one material is exposed at a time. There are models that have two emitters and two holes, such that two separate beams can heat two materials and perform co-evaporation. However, everything in the KNI is currently a single emitter. At the front of the assembly, there are some magnet coils which steer the beam and raster it around in the pocket. If we look at a top view of the pocket, imagine there's a material like gold in here. This blue path is the beam path, often called a sweep. This can get rastered around in a circle or zigzag or square wave or a variety of different paths, but the basic purpose of it is to heat the material evenly. The design of a sweep pattern will depend a bit on the thermal properties of the material, such as how well it conducts heat and what its melting point is. The Labline is a four-pocket evaporator which is restricted to the evaporation of titanium, platinum, gold, and aluminum. It is equipped with a manual transfer load lock enabling fast pump down. Depending on the thickness and number of layers, users can often finish a run in 1 hour or less. The system is equipped with a crystal rate monitor and two shutters, one above the hearth and one just below the substrate manipulator. Base pressure is typically between 3 e to the minus 8 and 7 e to the minus 8 torr. It has a long throw distance, good for liftoffs. Equipped with an argon ion gun for pre-deposition surface cleaning and etching, as well as ion-assisted deposition. Complex automated recipes can be made. Most users will find their needs covered in an existing recipe, but we can make something custom if you need. Before we start using the tool, there are a few quick things we need to check. Check that the cryopump temperature is approximately 12 to 13 Kelvin. Check that the red and yellow lights on the status light are not on. Green means everything is normal, blue means that a recipe is currently running, yellow means that an interlock has been tripped, and red means that a process has been aborted, either automatically or by the operator. On the left side of the electronics rack, you will see a small handheld controller. This is the Genius controller. Check that it says Automatic Operation. If it does not, follow the instructions posted directly above it for putting it into automatic. Check that the power supply for the electron gun is on. This is at the bottom of the electronics rack. Now we are going to look at the software used to control and monitor the system. Some frames remain constant no matter which screen you are on, such as the login, the message output window. This will show a log of everything you do and any interlocks or errors that cause aborts. These four tabs change the contents of the main screen. We are currently looking at the vacuum panel. Here's a digital representation of the status light along with a process abort button. These buttons run frequently used recipes. This is a simplified version of another window we will see soon. Don't worry about this as it's not of much use to us. These buttons go into the different sections of the system. Always stay in the operation section, as the other sections are more for advanced system details. Let's take a closer look at the vacuum panel. This diagram is a top view of the chamber, where the bottom screen would represent the front side, which faces you. This is the main chamber. Behind it sits the cryopump and a gate valve between the two. To the right of the chamber extends the arm for transferring samples. To the left of the chamber there is the load lock, again separated from the main chamber by a gate valve. The diagram shows all of the valves, which consist of 2 gate valves and 5 small angle valves. The status of any part of the chamber can be seen with green highlights. For example, the cryopump and its gate valve are both green. This indicates that the pump is on and the valve is open. You'll notice that there is a path to and from the rear gate valve to the load lock, with load lock high vac valve in between. The valve is green, indicating that it's open. The pipe from the pump to the load lock is green, indicating that it's under vacuum. There are 3 vacuum-related interlock switches. One indicates that the transfer arm is fully retracted. This means that it's out of the way and allows for movement of both the load lock gate valve and the substrate manipulator. This switch indicates that the chamber is under vacuum, and this switch indicates that the pressure difference between the load lock and the main chamber is low enough such that it's safe to open this isolation valve. The status of the chamber has now changed a bit. A moment ago we were looking at what would be an idle state. Both the load lock and the main chamber were at high vacuum, and all vacuum interlock lights were green. Now what we're looking at is the result of running the load lock vent recipe from the recipe buttons on the right. The load lock high vac valve is closed, and that part of the chamber is at atmosphere. Notice that the pressure differential interlock light isn't on. This indicates that it is not safe to open the load lock isolation valve, and so the system will prevent you from doing so in this condition. Now we would be able to open the door to the load lock and affix our samples to a holder inside, called a platen. This is the recipe monitor window, which pops up when you run a recipe. At the top it says the recipe name, which is load lock pump. This is immediately after I have hit the button for that recipe on the right side. This recipe is now running. The recipe monitor window shows you details about the recipe, such as which step it's currently in, remaining time for certain phases, and also allows you to have some control over it. Pause and resume, as well as abort, are the key functions. Notice that the roughing pump is now on, and the line leading towards the chamber is green. All of the valves that connect the chamber to the roughing line are currently closed. As load lock pump proceeds, the load lock rough valve will open to pump on the load lock. Once the pressure is low enough, the rough valve will close, and then the load lock high vac valve will open. This recipe will continue until the pressure between the load lock and the main chamber are low enough for the pressure differential light to go on. Now we can see that the load lock pump recipe is complete, as the recipe name is highlighted in the monitor window. The roughing pump has turned off, the load lock high vac valve is open, and the load lock is pumped down sufficiently to satisfy the pressure differential condition. Let's say now that we've put our samples in the load lock and pumped it down. We're now ready to transfer the platen holding our samples into the chamber for deposition. This is a representation of the chamber, as if you were viewing it from the front. This is the load lock. Inside sits the platen on a stage, which can be moved vertically. To the right of that is the load lock isolation valve. Inside the chamber we have the substrate stage, which can rotate and move vertically. To the right we have the transfer arm, which can reach across the chamber into the load lock and pick up the platen. The E-gun is below everything at the bottom of the chamber. The load procedure is as follows. 1. Make sure the substrate stage is all the way up. 2. Home the rotation position of the stage. This is done to ensure that the support rods aren't in the way of the platen being placed on it. 3. Move the platen stage up to its loading position. I'll describe this more later. 4. Open the load lock valve. 5. Move the arm over to the platen. 6. Lower the platen stage. This rests the weight of it onto the arm instead of the stage. 7. Fully retract the arm into the chamber, taking the platen with it. 8. Drop the substrate stage below the level of the platen. 9. Move the platen over the stage. 10. Raise the stage to support the platen. 11. Retract the arm, leaving the platen on the stage. And 12. Move the substrate all the way up. The unloading process is essentially the reverse of this. This shows all of the controls you'll need to transfer your sample. This wheel lets you move the substrate stage up and down. This wheel extends and retracts the arm. Here is a viewport with a shutter you can use to watch what you're doing. This is the load lock. Simply lift the top hatch when fully vented to open it. Beneath it is a wheel that you use to move the platen stage up and down. Let's look at sample transfers in more detail. When raising the substrate stage, this is the fully up position. Notice the green mark. Below the green mark, and you are below the level of the platen when it's on the arm. After you've opened the load lock valve, you will need to put the platen in the proper position for the arm to grasp it. The center of the platen has a groove in it that the arm needs to slide into, and by raising it to the proper position, it will do so without resistance. Raise the stage until the top of this brass ring rests just below the mark on the steel shaft. Then, slowly rotate the wheel to extend the arm into the load lock. Be very gentle when moving the arm. The moment you feel any resistance, do not push it further or you may damage it. This is very important. At the end of the load lock, there is a viewport window in which you can see the platen. If you have put the platen at the proper height for the arm, then you will see the arm in the center groove around the edge of the platen. The arm can now support the weight of the platen. Now we can drop the stage down, causing the platen to rest on the arm. Now we are looking through the front viewport on the main chamber. Retract the arm all the way in. This allows us to then move the substrate stage down past the platen so that we may rest the platen on top of it. Carefully move the arm over towards the stage. Then move the stage up slightly. Repeat this until you gently rest the lip of the platen on the substrate stage. Raise the substrate stage slightly until the arm is in the middle of the two lips of the platen. The arm is now no longer supporting the weight of the platen, and you will be able to retract the arm while leaving the platen in place. Now that our samples are loaded, let's move on from the vacuum screen to the deposition screen. This screen tells us about the status of E-beam power outputs, deposition rates, film thicknesses, as well as shutter, substrate stage, and crucible positions. The E-beam control section shows you the emission power. The set point is in white, and the actual value is in green. Below that, it shows you the deposition rate. Again, the set point is in white, and the actual is in green. It also shows the crucible position. The film thickness section shows you the rate, the current thickness, the remaining percentage life of the crystal, or quality, and some parameters specific to the material you are evaporating. The film thickness set point shows you the thickness of the film you've requested when you set up the recipe. The status of both shutters is shown on the button you can use to manually actuate them. These buttons will turn blue when their respective shutter is opened. This section shows whether or not the sample is rotating, and how fast. Finally, the process phase window shows us which phase of the deposition recipe we are in. Now we are going to go ahead and set up a deposition recipe. Hit the Run Recipe button. Once you do that, the recipe list will pop up. I've selected Deposit TI. Then hit Run Recipe, and the following window will pop up. In this window, I can put in the desired thickness in kiloangstroms. 1 kilangstrom is 100 nanometers. Below that, I can put in the desired rate in angstroms per second. If you have no idea what rate to select, then choose 1 as a default. Hit Continue Load, and the deposition process will start. Now we are in the middle of deposition. This screenshot is taken during the part of the process where the samples are actually being coated. Let's first look through the various displays, and then I will explain the things that occur leading up to this. The E-beam control section shows that the high voltage is on. You can see that the power set point and actual values are the same. It shows that we are in Crucible 1, which is where titanium is located. The rate is currently set to 1 and currently is 1. You can see that the substrates are rotating and that both shutters are open. Note that the process phase window says that we are in the deposit phase. This will continue until the desired thickness is reached, upon which both shutters will close and the power of the beam will ramp down. After that, the deposition is finished. On the last slide I said that prior to the deposition phase, there are phases that lead up to it. Starting from left to right, these sections outline the different phases. First, setup prepares everything for the beam to come on. The substrate begins to rotate, the calibrating values for the crystal rate monitor and the material about to evaporate are loaded. The hearth rotates the desired material into position, and the high voltage supply for the beam comes on. Next, the system goes through 2 ramp and soak phases. During ramp 1, the emission power is gradually ramped up to a value which is coded in the recipe. During soak 1, it will rest at that power for about a minute, depending on the recipe. It will then go into the second round of ramp and soak, where it will bring the power up a little bit more. After the ramp and soak, you will see the system enter a phase called shutter delay. During this phase, the shutter over the evaporator opens up. At this point, the crystal is now being coated. The system will adjust the power of the beam as necessary to stabilize at the evaporation rate you specified. And once that occurs, the shutter below the substrate will open. At that moment, all measured deposition is counting towards the layer thickness you specified. The shutters close the moment that thickness is reached. Lastly, it will enter the ramp down phase. It gradually turns the power down and stops the substrate rotation. The recipe is then finished, and you may unload your sample. There's a special note about the shutter delay phase. During this phase, it is possible for us to make a visual assessment of the sweep pattern, how much material remains in the pocket, and see evidence of a developing E-gun problem. During shutter delay, the shutter over the evaporator is open, while the shutter under the substrates is closed. Near the base of the chamber, there is a viewport with a shutter, and that shutter has a mirror. If you tilt it down to about 30 degrees from horizontal, you can see that there is a mirror on the underside of the substrate shutter. We can now see the reflection of the crucible at the bottom of the chamber. Use a pair of dark welder's glasses to look at this, as it is very bright and can damage your eyes. This image is too bright and overexposed to see any detail, but with darkened glasses you will be able to see the sweep in the material in the crucible. If we look at this representation of the crucible, the red region should give you an idea of the boundaries of the sweep. You should never see that the beam is striking out of this approximate region, as this can lead to damage of the crucible and evaporant parts. If you look inside and it appears as if there is a hole in the material, you should stop. Be careful not to confuse a small spot of molten material for a hole. Now that we're done depositing, we can unload our sample. Unloading is the reverse of loading, but I will make 2 notes about it here that should make it easier. After the motor position is homed, you will bring the substrate stage down so that you can slide the arm directly into the center groove of the platen. You need to do this by eye. Bring it down to approximately where you think it needs to be. Watch while you slowly and carefully bring the arm in. If you bump anything, then stop and withdraw. Once you've got it in the center, you can drop the stage down. As soon as you drop the stage down, the arm will take the weight of the platen, and you can then move the platen over to the right with the arm. The second note pertains to when you are bringing the platen back into the load lock. You won't want to raise the platen stage to the loading position. Instead, drop it all the way down and bring the platen in. Then, watch through the top and side viewport and adjust both the arm position and the stage height until you gently sit the edge of the platen down onto the stage. Then you will want to move the platen height to the loading position, thus restoring the fork in the center of the groove so that it is not supporting any of the weight of the platen. You can then withdraw the arm and retract it all the way back into the chamber, leaving the platen in the load lock. Let's summarize the entire process flow. Starting at the left, we will first load our sample. This involves venting the load lock, then affixing the wafer or sample to the platen, followed by pumping the load lock, and finally a manual sample transfer. Then we can begin to deposit. Start the deposition recipe, observe the sweep pattern during the shutter delay phase, and then monitor deposition. Please don't walk away for extended periods. Check in on your run every few minutes. After our deposition is complete, we will then unload. Perform a sample transfer, vent the load lock, remove your sample, then pump the load lock, and you're finished. One final note about monitoring the deposition process. Pay attention to the power of the beam and the rate. If you suddenly see that your power is increasing quickly and your rate is dropping, this is an indicator that the crucible is running out of material. Rapid fluctuations in power and rate can also indicate this. This is a reason to abort. During sweep observation, if you see that the sweep is outside of the proper region, you should also abort. If you have to abort, the main gate valve for the cryopump may close. Normally it should be open like this. If this occurs, quickly select the PC pump recipe from the frequently used recipes at the right side of the screen. This will open up the valve. Thanks for watching. If you have questions or comments, please email me at alexw@caltech.edu.